Okay, so any questions about the course, about the things we will do, etc.? So let's start with the conservation laws. Yeah, you should get ready to lots of indices, lots of mathematics, lots of integral derivations. Unfortunately, we will have them. So what was the problem? So let's first try to analyze the problem and try to find a strategy that would allow us to solve that problem. So what do we know? We know that there are forces acting on charged objects in an electromagnetic field. And these forces will be Q times E plus V cross B. Now, first, I would rather study the conservation of energy rather than the momentum, because studying the energy is relatively easy. We already know part of the answer. We already studied the energy stored in an electric field, for example, last semester. We will also derive that one, and we will also derive the energy stored in a magnetic field. I think we discussed it, but very shortly, we just passed over it. And then we also see that the energy of a system of charged particles and electromagnetic fields will be conserved. That we didn't discuss. So we only analyzed what is the energy stored in an electric field, what is the energy stored in a magnetic field, but we didn't really talk too much about conservation. We don't yet know whether the total energy of a given system is conserved or not. So that is what we will be discussing now. So if this is the work will be doing the force will be doing some work on the charged objects. Let's say this is the I object. Then of course the electric field and the magnetic field over there will be the electric field and the magnetic field at the position of this Qi. And the power that this force applies on our charged object, if you remember, power is the work done per unit time, and the work done is just F dot dl under a very small displacement. If you divide it by dt, this is F dot v. So the power given to point-like charged object moving in an electromagnetic field would be, let's just call it Pi. This will be Fi dot Vi, which is Qi times E plus Vi cross B dot Vi, Qi times Vi cross E. That's it. As I frequently repeated when we were discussing the magnetic field, what is the power of the magnetic field? What is the work done by the magnetic field? Zero. So there is no power delivered to my system due to the magnetic field. And it's also seen over here. If you take the cross product of two vectors, then that cross product is a third vector which is perpendicular to both of those vectors. That is how we define it. So this vector is perpendicular to Vi. If you take the scalar product of two vectors that are perpendicular to each other, that is zero. And here, this is a nice part also. This charge times the velocity is nothing but the current density. So I can generalize this to power delivered to a system of charges by just summing all these ones. But if I just sum over all those ones, that is nothing but dV, the integral over the volume. I'm sorry, this is not the cross product, this is the scalar product. E dot J. This is the power. But this is also nothing but the rate of change of the mechanical energy of the moving charges, of the point objects. They have some mass, they have some kinetic energy. So this is the work done on the object. The work done on these point masses will be equal to the rate of change of its, the work done on it will be equal to the change in their kinetic energy. That is the kinetic energy work theorem from your freshman years. So if there is a power, that just relates to the rate of change of the kinetic energy of my system. So this is what I call the mechanical energy. Well, if there is also gravitational force, which we are not taking into account over here, that you can also put it over here. So the rate of change of the mechanical energy, remember the mechanical energy we had defined as the kinetic energy plus the potential energy. The rate of change of the mechanical energy of a given system is equal to the power delivered to my system by all the other forces. So remember, the potential energy already corresponds to a force, but if the mechanical energy is changing, that means there is some other force acting on the system that is not described by this potential, and that other force is doing some additional work on my system. So that is why here I have this mechanical energy, not necessarily the kinetic energy, keeping in mind that you might be also putting the gravitational potential energy, for example, here. This is the power done by the electromagnetic force only. So what I would like to do is I would like to express this thing. I know that it's equal to the power, it's equal to this integral, but this integral already depends on the electric field and also the point charges also. I would like to write this as minus du em divided by dt. This is what I'm hoping to do. Where this, what I call um, this is the energy stored in the electromagnetic fields, should depend only on the electromagnetic fields and not on my point charges, neither on their currents. So that will be my strategy. If I can convert this equality into an equality of this form, then I can say that d by dt of u mechanical plus u em, this is equal to 0, which basically tells me that this sum doesn't change in time. Although my charges will be accelerating under the influence of this electromagnetic field, my electromagnetic field will be constantly changing in time. The energy of my particles will be constantly changing in time because they will be moving around. Nevertheless, although all these things are changing in time as my system evolves, this sum will be constant. It will not change in time. So that is what I will be heading towards. This is what I am hoping to obtain. If I can obtain such a relation, then I will see that energy is conserved. Right. Now the next question is, so the electromagnetic properties of our system are determined by the Maxwell's equations. Now the question is, do Maxwell's equations lead to such an equation? Yes, in principle, the Maxwell's equations describe everything about our system. So whatever property our system has, it should be derivable from Maxwell's equations, whatever electromagnetic property. So this is the answer that I'm looking for. Now the question is, does Maxwell's equation give me such an answer? So basically, this is my strategy. So I will not be just randomly manipulating my equations, hoping to obtain some conservation of energy. So there, I have a definite purpose. This is the purpose. If I can obtain such a relation, where this side already depends only on my point charges, my masses, this side should be independent of my point charges and masses. If I can do this, then I know that the total energy of my system, the energy stored in the mechanical energy of my point charges and the energy stored in the electromagnetic fields of my system is conserved. I don't know yet. We will show that it is actually the case. So are you ready?
Yani Nano'la
That will be our claim if this is satisfied. So we already made partially that claim last semester. We said that, okay, the energy stored, we can either assign it into the charges or assign it to the electric field. For example, the energy stored in a capacitor. Now this will be kind of taking it one step further. We will say that if we assign some energy to the electromagnetic field, in that case, the total energy is conserved. That will be the claim. Now, we will be using the Maxwell's equations quite often. So let's just write them down so that we will remember what they are. Divergence of E is equal to rho over epsilon 0. These are the electric monopoles or electric charges. Divergence of B, this is equal to 0. Or there are no magnetic monopoles or magnetic charges. Curl of E is equal to minus dB by dt. That minus is the Lenz's rule that we had. So the induced electric field will always, at least the induced current will always try to eliminate the cause that created it, that minus sign. Curl of B is equal to mu 0 J, or Ampere's law, plus there's also the displacement field there, this displacement current, which basically tells us that any changing electric field should be creating a magnetic field. So what we have, the rate of change in the mechanical energy of my system, we had already shown that it was equal to the integral over the volume of my system of E dot J. Now I'm trying to eliminate all the current, all the dependencies on my point charge. So I have to express J in terms of my fields. Well, I can already do that using the Ampere's law. The second equation on the last equation on the second line. You see the curl of B is equal to mu 0 J plus some E. So I can solve for J. So the volume integral of E dot, well, J is 1 over mu 0 curl of B minus mu 0 epsilon 0 d by dt. Which is equal to 1 over mu 0 dV E dot the curl of B minus dV epsilon 0 E dot dE by dt. Well, the last term is nice. So let us write it in a nicer form. I'm not playing with the first term yet. If I take the time derivative, epsilon 0 is constant, the derivative of E squared is just twice E dot derivative of E. That is what I have on the previous line. Well, I can take that time derivative out. Well, if you remember, this was already the energy density stored in the electric field in a capacitor. We already have that. If I take that time derivative out, what remains is an integral over all the coordinates. So this integral depends only on time. So the partial derivative becomes a total derivative. So this is equal to 1 over mu 0 dv E dot the curl of B minus d by dt Okay, so you see, if you remember what we are looking for a relation of this form. We started with the left-hand side. On the right-hand side, I have to write it that I'm trying to write it as minus the total derivative with respect to time of some quantity that depends only on my fields. Okay, that is, at least the last term has that form. Well, the first term doesn't have that form yet, so we have to be playing with it a bit. Now, also keep in mind, okay, there will be terms that I can just eliminate. Like, for example, if you end up having the volume integral of the gradient of some function of the electric and magnetic fields, if I take the volume to be infinite, well, this will be just 0. Because I can just convert it into a surface integral, okay, divergence of something. I can convert it into a surface integral, and assuming my surface is at infinity, the E fields and B fields at infinity will just go to 0. So that will be my purpose with the first term over here. Can I convert this into some gradients plus some term of this form? So that is what I will be trying to do now. Now let me look at that one. It just looks like 3 vectors. I have 3 vectors. Okay, I have some cross product, some scalar product, etc. So let me look at this one. What is the gradient of E cross B? Maybe the divergence of E cross B. Maybe this divergence will contain this term plus some other term which might be nicer. This divergence is just like this one. I can just, within the integral, taking the volume to be infinite, it just goes to 0. And this term remains over here, so it will allow me to write this term in terms of some other term, which maybe I will be able to write in terms as a total derivative. So what is the divergence of the cross product of 2 vectors? Well, if you don't remember, index notation. That is something you should try to use just to get familiar with it. Not something that you should try to avoid as much as possible. Use it whenever you get the opportunity. If you don't get the opportunity, invent some problems on your own so that you will use the vector notation, so you will get used to using it. So this is equal to derivative with respect to xi of E cross B, the I component. That I component is epsilon I jk, ej bk. Well, now I can take the derivative. This is epsilon I jk del I ej multiplied with bk plus ej del I bk. Now this is epsilon I jk del I ej multiplied with bk plus ej epsilon I jk del I bk. Inside those parentheses, I have the curl of the corresponding fields. So this is equal to curl of E, the k component of the curl of E multiplied with bk, plus ej multiplied with minus the curl of B, the j component. Do you know why I have that minus sign? Now, if you look at this Levi-Civita over here, the indices are I and K. I and K have J in between. So I have to move J to the front. That brings me a minus sign. The rest is the curl. So what we had shown, the divergence of E cross B is equal to B dot curl of E minus E dot curl of B. Now let's see what we were looking for. We were looking for E dot curl of B. So that is what we have in our expression over here, E dot curl of B. Now E dot curl of B is equal to B dot curl of E minus the divergence of E cross B. Now let's remember our Maxwell's equations. What was the curl of B? Minus del B by del T minus the divergence of E cross B. Well, great. Now we have another derivative, time derivative. This is minus del by del T of 1 over 2 B squared minus the divergence of E cross B. Now let's go back. This is the identity we have in our expression, in our derivation. We had an expression that involved this one. Now we could convert it into this expression. Well, it doesn't look simpler, but it suits our needs. Remember what we were looking for. We were trying. This expression appeared in an integral. What we were trying to do is we were trying to write this as a time derivative and a divergence. Because the divergence integrated over the whole space, since E and B, they both go to 0 at infinity, this just goes to 0 if we integrate over all space. Then we have what we were looking for. Let us rewrite it down. So this is our expression we started with. We started with the time derivative of the mechanical energy of the point charges. This was equal to minus the total time derivative of the volume integral of 1 over 2 epsilon 0 E squared and then we had 1 over mu 0 times that, the integral of that term, plus 1 over mu 0 times the volume integral of minus del by del T of 1 over 2 B squared minus the divergence of E cross B. Or let us just reorganize it slightly. This is equal to minus d by dt of dv 1 over 2 epsilon 0 E squared plus 1 over 2 mu 0 B squared. This is this term plus this term. And then minus dv ds dot 1 over mu 0 E cross B. Yes. We were integrating the divergence of some vector field over a volume. As Stokes' theorem tells us, if you are integrating the divergence of some vector field over a volume, here we have the divergence of some vector field we are integrated over a volume, that can always be written as the integral over the surface of that volume, the integral of that vector field over the surface of that volume. And then we can identify energy stored in the electromagnetic field as dV 1 over 2 epsilon 0 E squared plus 1 over 2 mu 0 times B squared. Well, in fact, these were both the expressions that we had derived before. This was, we could derive this energy stored in the capacitor. This is the energy stored in an inductor. But this time we don't make any reference to a capacitor or an inductor. What we are imagining is we have this region of space which contains our charged objects. Let's try to identify the volumes we have. You see, we have our system. This is a mechanical system. Our system of charged objects that are moving around. There are some electromagnetic field in the vicinity, etc. So the mechanical energy of these point masses will be changing due to the action of these electromagnetic forces. And that change is given by this expression. Now, of course, if we want to find all the change in the mechanical energy of all my point masses, this summation or integration should be over all my point masses. So this volume integral is over everywhere where J is non-zero. So it can be, for example, if I have my charges over here, in this volume, let's say over here, I can take that volume to be a bit larger volume. Because in some part of it, J will be 0 anyway, so the remaining will be just a contribution from this region. Or I can imagine this volume to be not just a bit larger, but I can take that volume to be infinitely large. Now, the difference between the two will be, since I have these charges over here, the electric fields or the magnetic fields that they create will not be limited to this finite volume. So if I'm interested in the total energy stored in my electromagnetic fields, I have to be integrating over all the volume, all of the universe. So if I want to identify the energy stored in the electromagnetic field, I have to take my volume to be infinitely large, this one. If I take my volume to be infinitely large, then at infinity, the E and the B fields, they will go to 0. And then this surface integral will be just 0. I'm left with the top part only. And that will tell me that du mechanical by dt is equal to minus du electromagnetic by dt, or d by dt of u mechanical plus u em is equal to 0. Now we have proof that Maxwell's equations predicts that the total energy of my system is conserved as long as I identify this integral as the energy stored in my electromagnetic field.
Mesela hani kablolu elektronun gittiğini düşündüğümüzde bir de şey yapıyor, hani direkt falan hızlı oluyordu, bunun bir ısı yayılıyordu. Burada nereye koyacağız onu, hani
Well, let's see. Good question. So we have this wire. Along the wire, the electric field pushes the electron around, so there's some heat in my system. What is heat? The kinetic energy of motion. Of what? Not the electron, of the atoms. The electron is colliding with the atoms, etc. So my system, my complete system here is basically electrons and the nuclei. All of them are my mechanical system. So when the heat is increasing, that basically is the kinetic energy of the atoms are increasing. That's what we mean by it's heated up. So their random motion is larger now. Mechanical energy has increased. So it is this part. It's in this mechanical energy of the point charge is making my system. Now the crucial thing in this derivation at least is that I'm not separating some charges and ignoring the other charges. I'm taking into account all the charges in my system, everything that can create an electromagnetic field, everything that will feel an electromagnetic field. If you just look at a part of a system, then of course this energy need not be conserved because some other forces are acting on them. So it's not just the electrons that I'm considering here, it's the electrons plus the remaining of the rest of the atoms. All of their mechanical energy is over here. So heat basically enters here. Larger heat basically means larger mechanical energy.
Hocam ben şeyi anlamadım. En başta şunu gördük ya. Yani bu böyle olması gerektiğini nasıl anladın?
Which one?
Bu
This one.
yazdığınız şey.
I didn't. I just made a guess.
İşte doğru olan şeyi nasıl tahmin ettik?
You don't. You see, okay, that's one problem about the lectures and using the books. We already know the answers. We are discussing things that we already have an answer for. So that's why I know this one. I know that I will be able to find something that will satisfy this relation so that I will be able to claim that energy is conserved. I already know the answer. If you have read your book already has the answer. But in general, you don't know it. So you just give it a try. You say that, okay, energy should be conserved. I trust energy conservation. Then your next question would be, okay, so what is the energy of the electromagnetic field? So this is just, if energy is conserved, then there's an energy in the electromagnetic field, there should be an energy in the mechanical point masses. So the sum should be conserved. Conserved means the time derivative is 0. So this equation should be satisfied. For this equation to be satisfied, you should be able to write the rate of change of the mechanical energy as minus the rate of change of some other kind of energy. But maybe Poyan thinks that, no, energy conservation, we should forget about it. So he doesn't give it a try. Or, I don't know, maybe Zeynep thinks that, okay, energy should be conserved, but the energy expression of the electromagnetic field should be equal to E dot B with some coefficient. She tried that one. She would fail. It doesn't work. So that's basically how science progresses. Everybody tries something. You speculate. You make assumptions. And you see where your assumptions leads you to. Sometimes they would lead you to some great theory. Sometimes they will just lead you to nowhere. And you forget it. You say, how many successful scientists do you know? How many scientists do you know, let's say? I mean, just give me an order of magnitude. Do you know 10 scientists? Come on, in the department there are 48 of them. Let's say, you know, in total, 58 scientists, 48 plus 10. let's say 100 scientists you might have heard about. Either they taught you or you read something about them in a book. Well, there were thousands or if not millions of scientists in the world that had lived. You don't hear most of them. Because most of the things they tried, even if they were correct, they didn't make revolutions. You only hear about the people that made actually the revolutions, but not the ones that led to that revolution. So how do you know this one? You don't. You give it a try. You take a chance. With more experience, you know what you should try. For example, if I would just look at two of you, and if she would say, okay, the electromagnetic energy should have this form, if she had said that. On the other hand, if you said that, okay, there should be some form of the electromagnetic energy that should satisfy this one, let me try to find that, I would say that she doesn't have enough experience, you have much more experience. The difference between this one and that one is experience. Because up to this point, you have made thousands of assumptions like this one, and you know that they fail. So you try to develop your more effective methods. Whereas for her, probably it's her third trial as a scientist. That's why you should try to find your own solutions, and homeworks, as I said, they are your playgrounds. Try your solution and make mistakes. Because that is how you will learn how to judge by just looking at the onset, at your first steps, whether it will lead you somewhere or not. Of course, the bad thing is that will cost you some points in your grades. Too bad. So that should lead me to think that, okay, I should reduce the weight of the homework. But if I reduce the weight of the homework, then you don't do the homework. Well, you see, very rarely, out of the lectures at least, you have a definite answer. You just try and see whether it works or not. And at least in physics, it's kind of clear-cut whether it works or not. In other things, well, you don't know. I mean, every attempt will have some positive sides and negative sides. Well, my impression is that at least giving a large weight to the homeworks does more good than bad. So I stick with it. Okay, any other questions?
Şu integral hocam hacmi infinity diye aldık ya, onu almak zorunda mıyız? Hani verilen hacmi alsak yetmez mi?
Now we will do that one. You see, if I don't take the volume to be infinite over here, well, that would basically mean that I'm not taking all of the energy stored in the electromagnetic field, but only the energy stored in the electromagnetic field within this volume. Some of the energy will be outside. So the total energy need not be conserved in that case. But it won't be conserved because since I'm considering the energy within this volume, maybe some of the energy is going out of that volume. So the total energy inside is not constant in time. It won't be constant in time. It will be changing because it will be flowing through the surface of this volume. So I should be able, still I can talk about energy conservation in general. But in this case, there is a total energy within this volume. That total energy within this volume will be changing, and the rate of change of the energy stored in this volume will be equal to the flow of energy through the surface. Okay? So let us write it in that way. d by dt of u mechanical plus dv some volume integral 1 over 2 epsilon 0 e squared plus 1 over 2 mu 0 b squared. Now this time, I'm not taking the volume to be infinite. It can be finite. So the mechanical energy over here will be the mechanical energy of the charges in my volume. There might be some other charges outside, I don't really care. This integral will be equal to minus ds of 1 over mu 0 E cross B. So you see, my volume is finite. Let's say this is the volume, this is the boundary of V. V is finite, the volume. The rate of change of the total energy, both the mechanical energy of the point masses and the energy stored in the electromagnetic field, its rate of change is not zero, because some of it might be flowing out of the surface of the boundary surface of my volume. So the rate of change should be equal to the total flow through my surface. Well, this is my flow through the surface. So this is the energy flux, energy flow through a given point on the surface. And I'm integrated over the all of the surface to obtain the total energy flowing through the surface per unit time. And that quantity, 1 over mu 0 E cross B, is what we define as S. This is our pointing vector. Now, if these expressions kind of look complicated, let's look at another case that we had already studied also last semester. Let's assume we have some arbitrary volume, V, with some charge density inside. So the enclosed charge inside this volume is just the integral of rho of r, the charge density over my volume. Now I can talk about the rate of change of this enclosed charge. Well, the rate of change of charge is nothing but the current, right? So let me write this minus I, that's the current through boundary of V. Well, why did I put it minus? Because I prefer to define the current as positive if it is going out of my volume. So if the current is positive, the current is going out of my volume, so the total charge enclosed will be negative. The rate of change will be negative. So if the current is positive, I want this to be negative. So that's why I put that minus sign. But the current passing through any surface, we had wrote it as minus the integral over the surface of the current density. You see, if there is such an equation, then you know that the charge is conserved. The total charge enclosed by a volume need not be a constant, but if it is changing, it should mean that the charge is basically passing through the surface to the other side, to outside my volume. So it is conserved. The total is still conserved. So here I have exactly an analogous equation. Here I have some quantity, which is some kind of a volume integral. So it is the total of something inside my volume. that quantity is changing in time because something else is passing through the surface. So this is what I identify as the energy inside my volume. So just like in this example of the charges, so this quantity over here is what we call the charge current, the current of moving charges. This quantity over here, I will call the current of energy. So energy is flowing through my system, through the surface. So that is why the total energy stored in my volume is changing with time, because it is flowing through the surface. But it is not changing because it's just disappearing from the universe. It is changing because it's just passing through the surface of my volume. So this is what we call the conservation law. Energy of the mechanical energy of point masses plus the energy stored in the electromagnetic field is conserved.
Peki J constant olmazsa yani sabit.
It's not constant. J need not be constant. J can have a different value everywhere. That's why I have an integral over here. If J was constant, I could take it out of the integral, and what remains would integrate to 0. In fact, if J is constant, then the total enclosed charge will not change, because whatever is entering from one side will be leaving from the other side, or whatever is leaving from the other side will be entering from the other side. Whatever is leaving through this surface will enter through this surface if J is constant. So I'm not assuming that J is constant here. And neither here I am assuming that this pointing vector is constant. It's changing with time. It can be changing with time, it can be changing with a position. Because you see, in general, E and B fields will be position and time dependent. Because all my charges I'm even considering cases here where my charges are moving in whatever complicated manner you can imagine. Well, you see, it could have been that I have some volume, and within this volume, the time derivative is 0. So in that case, that would just mean that nothing is flowing out. So the surface integral should be 0. But what would be interesting is if the time derivative of this quantity is non-zero, and I cannot write it as a surface integral. In that case, it would tell me that there is some kind of a non-conservation over there. Because if a quantity is conserved, the total amount of quantity within some volume, its rate of change should always be equal to the surface integral, if it is conserved. If there is no such surface integral, then there is no conservation. It's not conserved.
Hocam şimdi buna göre bu volüme baktığınız zaman volüm ışıma mı yapıyor?
We will be discussing what is radiation, but that is one possibility. Because if you look at the lamps, let's say, what's the lamp? They are just rods, cylinders of some 1 meter length, 1.5 meters length, let's say. So just imagine that volume. So what is happening within that volume is you are sending currents. You are inputting some energy to my system. And there is some radiation coming out. We will see that radiation is nothing but electromagnetic waves. So is the energy conserved? How can we test that the energy is conserved? So first question, is the total energy inside my volume constant? I look at my lamp, nothing is changing in time. So within the volume, the mechanical energy is the same, The energy stored in electromagnetic energy is same. So this sum is 0. This sum is constant. Its time derivative is 0. So that means that the surface integral over here should also be 0. Now this surface integral will be due to the current that I'm sending in and the radiation coming out. So whatever I send in should be coming out. So that the surface integral will be negative at some parts of my surface and positive at some other parts of the surface. So the sum will be 0. Okay, this was the easy conservation law. Now we have a more complicated one. You see, our initial motivation was conservation of momentum. So this tells me that the energy is conserved, fine. I mean, even beforehand, we didn't really have a simple example in which we could claim that energy was not conserved. Now let's look at the conservation of momentum. Now, we already have an experience in conservation laws. So that is our experience. Now we know what we are looking for, more or less. So I would like to obtain an expression of this form. So the rate of change of, let me put mechanical momentum, meaning that it's the momentum of moving charges. That's just the mass times the velocity of each one of the point charges summed over all of them or integrated over all of them if you have the continuum. Then I should be able to identify momentum of the electromagnetic field. Well, let me just do one more thing. I know that each component of momentum should be conserved, not separately. Well, each component should be separately conserved. So rather than looking at the momentum vector, I can look at the I component, the x component, y component of the z component. So this should be equal to, well, I can keep the volume finite straight away from the beginning. So this should be equal to minus some surface integral. So if I have a finite volume, I calculate the total momentum inside my volume. It should, if it is changing, it should mean that there is some momentum flowing out of my surface. So I should be able to write it as a surface integral of, let me say, use the symbol T. Of course. That is what, I mean, you see, I'm first deciding on my strategy. How will I attack this problem? So I'm just first putting my aim. So I'm aiming to obtain such an expression. This is the expression that I will try to obtain. And I will try to identify what this one is, what this one is. But there is one more problem here. You see, the x component of momentum in general will be independent of the y component and the z component. So for x component, I should get one t. For y component, I should get another t. For the z component, I should get another t. So that vector t should also have an x, y, z. We will discuss. I mean, you see, for the time being, I don't know. I mean, what I'm looking for is, I know that well, I know this one. It's just mass times velocity summed over the particles. If I can obtain such a relation, then I can claim that electromagnetic fields also have a momentum, and the total momentum of the system is conserved. Then, of course, there is a problem. In the previous example, in the case of the energy conservation, we first looked at the infinite volume limit, and in the infinite volume limit, we could have the mechanical energy plus the electromagnetic energy stored in all of the universe is conserved. That's what we derived. And then we said, okay, maybe not take the energy. Let's not talk about the energy in the all of the universe, but let's just look at the energy in some finite volume. And we said that, okay, the energy in some finite volume will be, the conservation will tell me that the energy in that finite volume, its time derivative need not be zero, because some of the energy can be flowing out of my volume. But that flow I should be able to write in terms of a surface integral. And then we said that, okay, this is the flow of energy. Well, we can do the same identification over here, more or less. If I take a finite volume, the total mechanical energy, the total linear momentum within that volume need not be conserved, because some of that momentum might be flowing out. And this is the direction of the momentum flow. You see, there's this weird part. And let's discuss that weird part also, and then we can go. Yes? I'm not taking the component of T. No? You see, for each component of linear momentum, I have a vector. So basically, what I'm calling this Ti, this is a vector. This is equal to Txi in the x direction, Tyi in the y direction, Tzi in the z direction. It's a tensor, yeah. But just don't freak out because you heard the word tensor. Now we will discuss what that would mean. Let me first explain what that means, and then we will see. Let's look at a wave. Hold it. Unplug it. And hold it. Hold it there. Please, so that everybody can see. You see, here I'm creating a wave. Okay? Up and down. What is the direction of the momentum of this wave? Of the momentum of the particles oscillating?
Up and down.
They're moving up and down. Their momentum is moving up and down. But the wave, at least let's say this one. No, you don't move. But the wave is moving in that direction. So this wave is carrying momentum in that direction, but the momentum it carries is in the vertical direction. So a momentum, let's say, in the y direction is carried in the x direction, let's say. This is what that tensor or whatever that expression is. So you see, if you are talking about the x component of the momentum might be flowing out of my surface, but it might be flowing out in the y direction. It is what this Txy will mean. Okay, so there's a y component of the momentum flowing in the x direction, or it might be flowing in the y direction or the z direction. For point particles, if the momentum is in this direction, the momentum is flowing in that direction. That was kind of obvious. But for waves, that connection breaks down. Yes?
In the right-hand side, you have dot production of
Yes.
two vectors, so it's a scalar, but left-hand side, you have momentum, which is...
No, this is also, you see, I'm taking one component of momentum, which is just a number.
This is the
One component, this is a number. Time derivative of that component, the x component, that is a number. Here, for that component, I have this vector, another vector. I'm taking the scalar product, so this is again a number. That is why although I started with the vector momentum, I converted into components.
But here, we have in the right-hand side, you have the component of the vector t.
No. You see, this is what I mean by Ti. For each I, it is a vector. It's not the I component of the T vector. For each I, it is a vector. You see, for components, I don't put vector signs. So in a sense, this is, okay. This is a row of a second rank tensor, let's say. I can say that it's the X row, the Y row, or the Z row, but each row still has all the three components. Now, we will drive the explicit expression of it, write it as a matrix, and hopefully, in that case, it will be more easy. You see, we need 9 expressions to describe the momentum flow. In which direction does the X component of momentum flows? It will have an X component, Y component, and a Z component. For the flow of the X component of the momentum, I have 3 numbers. So for the X component of momentum, I have a momentum flow which is a vector. For the Y component, I have a momentum flow which is a vector. For the Z component, I have a momentum flow which is a vector. So for each I, this is a vector. Now, this is another example where your notation becomes important. You see, I don't put vector signs in components. But here there is a vector sign because this means a completely different thing. If I would like to put both a vector and an index, I would have used this one. You see, Ti is not equal to, because this notation would mean I have this vector over here, whatever that vector is, I'm taking the I component. I'm not doing that. This is different. Sometimes you will see this notation. Meaning that it's a double vector. Each component has 2 vector indices. But I would rather avoid that notation.
It also means the vectors have 2 bases, right?
2 directions. Bases are something different. Now, okay. Next, on this Wednesday, we don't have a recitation, or do you want a recitation? I mean, if you want to discuss these things, we can come together. But, I mean, there is not really an example that we can solve. So on Friday, we will just start from here.